Hey, welcome back everybody. In our next unit, we're going to work with logarithmic and exponential functions. But before we can build the idea of a logarithm, we need to be familiar with what function operations are and specifically what a composition function is. And that's what we're going to work on in this lesson.
So we've already worked with functions a little bit and function notation. You might remember that when we use this function notation f of x, that just means that we're giving the name to the function f, and anything inside that parentheses is what we're going to plug into the function. So you can add and subtract and multiply and divide functions just like you would add, subtract, and multiply and divide polynomials. So here's a couple of short examples on how that works. This notation f plus g of x simply means we want to take the function f of x and add on to it the function g of x. And that's as easy as adding those two expressions together. So that's the same as 7x squared minus x plus 1, our function f of x. And we're going to add on to that function g of x, which is 3x minus 8. And of course we can combine those by combining like terms. And so we end up with f plus g of x, giving us a new function that is 7x squared minus x plus 3x plus 2x and plus 1 minus 8 minus 7. And we're done. We can add functions in that way. Similarly, we can subtract functions. F minus g of x would simply be the function f of x minus g of x. Pretty intuitive, so we're going to take our function f of x, 7x squared, minus x plus 1, and we're going to subtract from that g of x, which is 3x minus 8. Now be sure to distribute that negative sign when we combine like terms here. But f minus g of x will be equal to 7x squared. Here we have negative x minus 3x minus 4x, and plus 1, that'll become a positive 8, plus 9. And we're asked to find the domain of these functions. We built two functions. Both of them turned out to be quadratics that open upward. And since they're just quadratic functions, there's no domain restrictions here. There's no fractions, and there's no roots. So for both of these, their domain is all real numbers, from negative infinity to infinity. Now, in addition to adding and subtracting functions, you can multiply and divide functions. So, suppose we want to find h times g of x. You can guess what that is. That's simply the function h of x times the function g of x. So, that's going to be 6x minus 16 times the function 3x minus 8. And if we multiply those two binomial functions together, we get and so we can build a new function by multiplying two functions as well. 18x squared minus 96x plus 28. And for the domain, notice that this is simply a quadratic. It'd be some sort of a parabola that opens up. And so the domain would be all real numbers from negative infinity off tending towards infinity. And of course, if we can add, subtract, and multiply functions, we can also divide functions. What will f divided by g of x look like? Well, sure enough, that just means we're going to take f of x and divide it by g of x. So that's 7x squared minus x plus 1 over 3x minus 8. Now generally we'd want to do any factoring and canceling, but the top is prime, and so there's no reducing to do there. We can conclude simply that f divided by g of x is the rational function 7x squared minus x plus 1 over 3x minus 8. Okay, note that there is a domain restriction here. We've got a rational function and the bottom can never equal 0. So we have to acknowledge that 3x minus 8 can never be equal to 0. And if you solve that, you'll find that x can never be 8/3. We can plug any other number into f divided by g of x, but not 8/3. Therefore, the domain is from negative infinity up to 8/3. And from 8/3 up to infinity. We just have to skip over that point, 8/3. We can also express division in a different way, h over g of x. So just a different type of division sign there. So we're going to have h of x over g of x. So that's going to be 6x minus 16 over 3x minus 8, but we're not done. In this case, we get a rational function that does simplify. That top factors a little bit. The top has a common factor of 2, a GCF that comes out, and we're left with 2 times 3x minus 8 over 3x minus 8. So those 3x minus 8s end up canceling off, and we end up with simply the function 2. Now for the domain, even though the function turns out to be just 2, there is a little hole in this function, and that is the place where the denominator could equal 0. So, since 3x minus 8 cannot equal 0, we know that x cannot equal, add 8 and divide by 3, 8/3. And so our domain of h over g of x is negative infinity up to 8/3, joined with all the points on the other side of 8/3, 8/3 to infinity. Just one number there that we're not allowed to plug in to our function. Now, in addition to adding and subtracting, multiplying and dividing functions, there's another operation that doesn't exist with real numbers, and that's called composition. What it means is to combine two functions by doing one function and then immediately another. So there's a new mathematical symbol for you here. A little circle like that isn't an O, it's just a little circle. And that's the symbol for a function, just like plus tells you what to do, minus tells you what to do, multiplication sign, or division sign. Those all tell you what to do. Well, so does this. And what it means is we're going to plug one function right into another. So we're going to plug a number in to function g. And then as soon as we get that output, we then turn around and plug it into function f. And the way we say that is we say we want to evaluate f of g of x. So what you're actually doing is you're starting out with a number x. That's your input value from your domain. That goes into your function g, and it'll put some output out. Then whatever g of x is, the output of g, that gets fed into the function f, and the output then is f of g of x. So let's take a look at an example. So we need two functions to have composition. F of x equals 2x. So let's evaluate for these two functions. F of x equals 2x plus 1 and g of x equals x minus 4. Let's find f of g of 9. Now what I like to do is I always like to rewrite the composition function. Instead of using that little circle, I like to rewrite it like this. For me, that's easier to think about. Now we're going to insert a 9 into our function. So the first thing I need to do is figure out what g of 9 is. So I'm going to step over here for a minute and just note that g of 9 is equal to 9 minus 4, using our g function. And 9 minus 4 is 5. So therefore, g of 9 is equal to 5. Now, that becomes the input into the outer function. So f of g of 9 is the same as f of 5. And f of 5 is 2 times 5 plus 1. And so apparently f of 5 is equal to 11. Then we can conclude that f of g of 9, which was the 9 plugged into g and its output plugged into f, is equal to 11. Here's another one. We can actually just find out what the function is. So if we want to find not f of g of 9, but just f of g of x, we'll again rewrite that and describe it as f of g of x. But we know what g of x is. G of x is x minus 4. So that means instead of writing f of g of x, we can write f of x minus 4. So that means we're going to take x minus 4 and plug it into the f function. F of x minus 4 is equal to 2 times our input. Here our input is x minus 4 plus 1, which is 2x minus 8 plus 1. And we can conclude then that f of g of x, g plugged into the f function, is 2x minus 7. Now a logical question to ask after that is, well, is g of f of x the same thing? That is to say, if we switch the order of f and g, do we get the same value? Well, let's check that out. Let's evaluate g of f of x and see if we get the same result. G of f of x is the same as g, but the f function plugged into it. So that's the same as g of f of x, but f of x is 2x plus 1. So we're going to plug 2x plus 1 into the g function. G function says you should take your input of 2x plus 1 and subtract 4. And so g of f of x, which is g of f of x, is equal to 2x plus 1 minus 4 minus 3. No, they're not the same. In general, we can't switch the order of f and g. That is to say, this operation is not commutative. They are not generally the same thing. So with that in mind, let's do one more problem. Let's evaluate g of f of negative 2. This time we're going to plug negative 2 into f and then g. So g of f of negative 2. Well, let's stop off to the side here and figure out what f of negative 2 is. F of negative 2 is equal to 2 times negative 2 plus 1, which is the same as negative 3. So g of f of negative 2 is the same as g of negative 3. And so g of negative 3 is equal to negative 3, our input value, minus 4, which is negative 7. So we conclude that g of f of negative 2 yields negative 7. Negative 2 plugged into f and its output plugged into g gives us negative 7. Okay, here's 2 for you to do for practice. Pause the video, go ahead and work these 2 out, and then start it up again and we'll work through the solution. Alright, here we go. F of g of 8. So, f of g of 8, we got to go over to the side here and figure out what g of 8 is equal to. G of 8 is 2 over 8 cubed. It's a pretty big denominator. G of 8 then is equal to 2 over 512, which is the same as 1 over 256. So g of 8 is 1 over 256. So f of g of 8 is really the same as f of 1 over 256. So f of 1 over 256 is 1 over our input value, and our input value is 1 over 256. So we're taking the reciprocal of 256 two times there, and we can conclude that f of 1 over 256 is 256. Therefore, f of g of 8 is equal to 256. Okay, and the solution of g of f of x, remember, that's the same as g of f of x. It's easier to think about that way. We want to plug the f function into g. So that's the same as saying I want to take the g function and plug 1 over x into it. Well, g of 1 over x, that's going to be equal to 2 over our input value, 1 over x, to the third power. Now we're dividing by a fraction here, so we can just as easily multiply by the reciprocal. So we can take and multiply that by 2 times x over 1 to the third. And we can then conclude that g of f of x is equal to 2x cubed. Okay, well, there's no limit to how many functions you can compose with one another. For example, if we want to find f of g of h of 2, we can go ahead and do that. Here we go. So this is the same as f of g of h of 2. Well, let's figure out what h of 2 is here. H of 2 is 3 times 2, which is 6. So we can replace h of 2 with 6. So f of g of 6. Now we can go ahead and figure out what g of 6 is as well. G of 6, that's equal to the square root of 2 times 6 plus 13. In other words, that's a square root of 25. That's equal to 5. So this becomes f of 5. And f of 5, we can calculate that as well. So f of 5 is 4 over 5. And so apparently we can conclude that f of g of h of 2 is equal to 4 fifths. So h of g of f of x, that's going to be h of g of f of x, we now know is 4 over x. H of g of 4 over x, that's going to be h of, okay, what does the g function have us doing? Our g function has us taking the square root of our input value times 2, and then we add 13. So h of g of 4 over x is the same as h of 2 times 4 over x plus 13. Now we can simplify that just a little bit before we go any further. We can say that that's the same as h of 8 over x plus 13. Okay, and finally, we're going to take that root 8 over x plus 13 and plug it into the h function. Our h function says that we should take our input and multiply it by 3. So 3 times the root of 8 over x plus 13. Okay, the next thing we can do is exactly the opposite. Given a certain function h, we can break it into its parts. We can decompose it. into two separate functions. So we want to find f and g such that h is built out of f and g. So, in other words, we want to figure out what h of x is if f of g of x equals 8x minus 1 cubed. So, here's the key. There's always going to be an inner and an outer function that's somewhat evident here. 8x minus 1 is sort of the inside function here, and g of x is the inside function here. On the other hand, there's sort of an outer function as well. F is the outer function, as is the act of cubing our input. And so we can conclude that our inner function, g of x, is equal to 8x minus 1. And we can also conclude then that our outer function simply takes our input and cubes it. And that's that. Now you can check that with very little trouble. Go back and make sure it actually works. Let's check to verify that f of g of x actually gives us our h of x function. So f of g of x is the same as f of g of x. And so that's the same as f of g of x, which we said is 8x minus 1. And our f function says take that value and cube it, and so that would be sure enough, we got h of x. Okay, one more quick one. Let's find f and g such that f composed with g gives us the function s of x. Here again, we just want to focus on the inner and outer function. We want s of x to be f of g of x, or in other words, f of g of x. So that's going to be equal to the square root of 3x minus 7. Okay. There's more than one way you could break this down, but one way would be to say our inner function, g of x, is 3x. And so we could conclude that g of x would be 3x. And then we could go ahead and say that our outer function, f, is taking the square root of our input and subtracting 7. And so f of x would be equal to the square root of our input value minus 7. An alternative to that is if you call the inside function g the entire square root function. You could also say that g of x is equal to the square root of 3x, and that the outer function, f of x, simply has us taking our input and subtracting 7. That's an alternative solution. The problems you do on WebAssign will be set up in a way that there's only one possible solution. Okay, you do this one for practice. Pause the video, go ahead and find out what f and g are so that they compose to give h of x, and then we're going to wrap up this lesson. Okay, here's our solution. F of g of x, which is f of g of x, equals 7x cubed minus 4. Here the parentheses are really the tip-off. It looks like our inner function, g, is the 7x. And the outer function, f, is to cube that input and subtract 4. Okay, that's it. But let's just check that. These are pretty easy to check. So, f of g of x, let's verify that that's the case. F of g of x would then be f of, our proposed g of x is 7x. So that would be f of 7x. And f of 7x is equal to our input, 7x cubed minus 4. And sure enough, there it is, 7x cubed minus 4. That's the function we wanted. So we're set. Okay, last thing to consider here. What if we have graphical type functions? We usually deal with equation type functions, but if we have a graphical function, we can still answer the same types of questions. So f plus g of negative 4. F plus g of negative 4, this goes back to the beginning of this lesson. That's the same as f of negative 4 plus g of negative 4. So let's figure out what both of those are. The f function evaluated at negative 4, the pink one is our f function, so we're right there. There's our point. Looks like we're at the point negative 4, 3. And so with an input of negative 4, the f function becomes 3. That's our output. G of negative 4, though, is down here at the point negative 4, negative 4. So when we have input of negative 4 for g, our output is negative 4 as well. So 3 plus g of negative 4, which is negative 4, we can conclude that f plus g of negative 4 is negative 1. Okay, f times g of 2, that's going to be equal to f of 2 times g of 2. So we can go to our graph. F of 2 is the f function evaluated at 2. That's right down here. Apparently that point is 2, negative 2. So our output of f of 2 is negative 2. And we want to multiply that by g of 2. The g function evaluated at 2, right there, looks like an input of 2 yields an output of 1. So g of 2 is 1. Therefore, f times g of 2 is negative 2 times 1, or negative 2. And finally, f of g of negative 3. That's equal to f of g of negative 3. So we have to first figure out what g of negative 3 is. G function evaluated at negative 3, right there, negative 3, comma, negative 2. So apparently when g has an input of negative 3, the output value is negative 2. So that means we want to evaluate f of negative 2. Well, what's the f function evaluated at negative 2? It's a different point here. So the negative 2, the f function is right there. Apparently that is negative 2, comma, 3. So when our input is negative 2, our output is 3. So f of negative 2 is 3. So apparently f of g of negative 3 equals 3.
Okay, well, that wraps up this lesson. Now we're going to build on these ideas directly in our next unit, but the idea of a composition function is very important so that we can build the idea of an inverse function, which we'll do in our next section. So get help if necessary with your web assigned work, and we'll see you in the next lesson.